Alrighty, welcome back to another lecture slide series, whatever you want to call it. I don't know. But today we're going to talk about more specific details about the planets, as well as go over some basic vocab about the different forces that are involved in these planets and their orbits and things like that. Probably going to be a lot more information than you ever wanted to know about some of these planets, but that's okay. That's why we're here. We're here to learn. So quick brain warm up, test yourself. Remember, you do need to know the order of the planets. This should be common knowledge for most human beings. Okay, remember there are 8 planets. Know their order from closest to furthest from the sun. Make sure you remember what the 3 criteria are for a planet to be a planet, like a full planet like Earth or Mars, and not a dwarf planet like Ceres or Eris or Haumea or Pluto. Okay, remember there is a very clear distinction there. What is keeping you on the ground right now? Why are we not just floating off into the abyss? Why are we not just floating under the ceiling? All right, well, that same force is also what's keeping the planets in orbit around the sun. And then think about those orbits. Do you know what shape the planets are orbiting in? We've touched on it briefly, like the intro slides, but we haven't gone over it into great detail yet. But it is a very important and distinctive shape, so pay attention to that. And do you remember the difference between a rotation and a revolution? Remember, these words cannot be used interchangeably. They are not interchangeable. They mean different things. Remember, Earth rotates on its axis like a top. Okay, think of a spinning top. That's a rotation. A revolution is the Earth going around the sun. It revolves. So one revolution is 1 year. Okay. And then, of course, you got to have a favorite planet. Everybody has a favorite planet. Mine varies on the day. Most days it's Mars, but also Jupiter is right up there because Jupiter and Mars are pretty cool. Third place would be Saturn. Mercury is the one planet I have major beef with. You will get into that. I don't like Mercury. I think it's a glorified rock. Anywho, all right, let's get into some of these basic terminologies we need to talk about. So some of these are terms you should have heard in your prior physical science class or chemistry class, or heck, even in biology, we talk about mass and density and things like that. So these are common science terms you need to accept and realize they're a part of your life, especially in this class. And the reason I'm going over these now, before we talk about the actual planets, which is kind of the cool side of things, is because I will use the term like mass or gravitational force or things like that a lot when I'm talking about these different planet characteristics. And if you don't know the difference between mass and weight, problem. All right, so first of all, mass is how much matter is in an object. This does not change. So think matter is atoms and molecules. So what makes you a person? What makes this desk a desk? Okay, the number of atoms and molecules don't change, regardless whether they're here on Earth or if I take this computer and I go to Mars with it. It doesn't matter. Okay, it's still gonna have the same number of atoms and molecules. So that is the mass. Now, there are different units of mass in science. For this class, or mainly, especially since we're talking planets and things like that, we're mainly going to focus on kilograms being our unit. We abbreviate that with kg. Now, mass is directly tied to weight. So weight is when you take in the force of gravity. So here on Earth, we are at 1g, 1 gravitational pull. That's what we are used to. That's what we have evolved into. That's what we are comfortable with. If you go to a smaller planetary body like the Moon or Mars, less gravity, less gravitational pull. Larger planetary body, more gravity, more gravitational pull. You're going to feel heavier. You're going to be harder to move. So say hypothetically, humans could go to Jupiter and exist without, being killed by the horrible radiation. Jupiter is a massive, massive planetary body. We'll get into that. That force, the reason, Jupiter and Saturn collect so many moons because there's such strong gravitational pulls. That force is going to flatten us, because that's what we're adapted to, is 1 gravitational pull. They are way above that. Okay. So gravity, remember gravity, the formal definition is the force of attraction between 2 objects, the Earth and the sun, the moon and the Earth, you and the ground. Okay. So generally speaking, just like I was kind of hinting at, the larger the mass, so the more stuff there is, the more atoms and more molecules, and the closer the distance between those 2 objects, the more of a pull there is. It's also a force of acceleration. So think of accelerating on the highway, right? You're moving forward, you're progressing, right? For this class, we are going to use either meters per squared, meters over squared, meters per second squared. I can stop to because I can. Or we're going to use newtons per kilogram. Those are how you write those out. And if you don't know what this little sign here is, that means like raised to the second power, so squared. Okay, so this is where weight comes in. So wherever you are, how much stuff you are made of, or whatever you're looking at, how much matter it has, how much mass it has, that is going to be influence the weight, because the weight is essentially taking the force of the gravity times the mass. So this is what is going to change. This is what is going to be variable. So you're going to have, say you are an astronaut, you go to the moon. You are going to have the same mass, but you are going to weigh less because there is less force pulling you down to the surface. That's why astronauts, when they go to the moon, if you look back at the old Apollo videos and things like that, they look like they're gonna hop in, they can hop really high. Like, and keep in mind, those EVA suits are heavy. Okay. And that is a benefit when we're talking for smaller planetary bodies. We'll get into that later on with the missions and things like that. But that less of a pull makes it feel like you weigh less. Okay. And then density. Density is another one that it comes up into play when we talk about these planets. So density is how much matter, how much stuff you shove into one specific volume. Okay. Density comes up with a lot of these planets. Like Saturn is the most least dense planet. Now, we know that because of its composition and all that. And we figured out how much matter there is versus its volume. That's how we know these things. Okay. So generally speaking, just because of how physics is physics, gas giant planets, the Jovian planets, are going to be much lower in density compared to Earth, Mercury, Venus, and Mars, our terrestrial planets. We are a higher density planet, which means there is going to be more stuff packed into a specific volume. So remember, mass versus weight. You cannot use the terms interchangeably. I know sometimes it's tempting, okay? Like when you go to the doctor, they are measuring your weight. Okay, those scales you stand on are adjusted to the force of gravity here on Earth. If we ever set up a settlement on Mars, we set up a medical clinic, which we should, those scales, or whatever scales they use in laboratories or what have you, are going to have to be adjusted to that gravitational force on Mars or the moon or whatever it is. Okay, so when you go stand on the scale of the doctor, it's adjusted to 1G. So it's taking into account that force, and it's basically trying to figure out how much stuff you're made of. Okay, and that's what spits out that number of your weight. All right, so make sure you know the difference between weight and mass. I'm pretty sure that's a quiz question. Okay, there's a cool infographic I found online kind of to show you what you would weigh on other planets. Remember, weight is mass times gravity. Okay, so, yeah. So that's kind of the how they got these numbers here. So let's see. So they started on this one, they started for Earth is 100. So it's a nice round number. We like that in science sometimes. So you can compare these numbers. Venus, remember, Venus is Earth's sister planet, the evil twin. Pretty dang close. 91 versus 100. That's not much of a noticeable difference. Now, so if you go to Mars, your weight is going to be 38 pounds. It's just over a third of 100, right? Whereas if you go to the moon, you'll be about 16 pounds. It's kind of crazy. All right, so I broke up these slides into kind of different segments. So we talked about the objects of the solar system and where things are in relation to the big landmarks of asteroid belts, Kuiper belt, Oort cloud, all those. And remember the inner planets, we call those the terrestrial planets, Terra meaning Earth. Okay, these are all planets you can theoretically land on and stand on. We're not going to talk about the atmospheric conditions and what that does to a human or not, but whatever. Terrestrial planets you can land on. There is a surface. They are rocky bodies, okay? So we're going to talk about the terrestrial planets first, and then we will talk about the Jovians or the gas giants. Now, if we were doing this live in class, what I like to do is kind of throw it back to my planetarium days and have you all pick which planets we want to look at in which order, whichever order. It makes no difference to me. But because I don't have a live audience beyond King Tut and Nefertiti, who don't seem to have many opinions right now, I'm just going to go in order. All right, first up is Mercury. It is the first planet from the sun. It is the smallest planet. It does not have any atmosphere. It does not have a moon. It does not have any rings. If you look at these pictures, okay, you can see it's covered in dents, basically craters. Okay. These are two images of Mercury, just with like this one is kind of a layered image, so we could remember those words. Remember the electromagnetic spectrum we talked about, and how there's different forms of light, different energies. Okay, we can take different kinds of pictures, ultraviolet, infrared, etc., and we can kind of stack them, make these really, really pretty images of different planets and things like that out there. It doesn't mean these are false color images. It means we have stacked multiple images together to produce this kind of image. Okay, it's like this is like a visible light, what you would see. Either way, you can see this thing is covered in craters. And what's cool about Mercury, I'll give it a little do. I'll get into my anti-Mercury thing in a moment. What's cool about Mercury is the craters are actually named for artists, musicians, authors, etc. Like there's actually a crater named after Dr. Seuss. So that's pretty cool. All these planets have very distinguishing kind of cool sub features like that I like to look at. We suspect there may be water ice at the north and south poles, which are, again, in those really deep craters, because guess what? When you're in a really deep crater, you don't ever see the sun. So it's permanent shadows, which means it stays frozen. Even though it's so close to the sun, if you're in a permanent shadow, it's kind of crazy. Because if you look at the temperatures down here on Mercury, this is one of the wildest temperature changes. So if you are in direct sunlight on Mercury, the temperatures get up to 800 degrees Fahrenheit. But if you cannot see the sun, if you're in a shadow, if you're down in like one of those really deep craters, trying to get the proposed water ice, it's down to negative 290 Fahrenheit. Cold. And a lot of people go, oh, if I were to just ask you or any random person on the street, what's the hottest planet? A lot of people are going to say Mercury because it's right next, it's the closest to the sun. Obviously, it should be the hottest, but it's not, because it doesn't have an atmosphere, which means it doesn't retain that heat. Okay, that's a big thing. The atmosphere here on Earth, think of it like a blanket. It keeps us, it's a nice warm hug. Okay, it keeps all of our heat here that we want, until we put too much carbon dioxide in the atmosphere, and then suddenly we have too much of a blanket. We can't get rid of it. Anywho, more on that later. So Mercury, named after the Roman god of swiftness, basically. If you know your Greek or Roman mythology, we're talking Hermes is the name most people recognize him by, especially if you've read or watched Percy Jackson. He's the guy with the sandals with the wings on them. That's why he was so fast. So because it's the fastest planet, its revolution, meaning it's 1 year, it's 88 Earth days. This thing is hauling. Okay, it is all the way around the sun. Okay, so just imagine 1 year is equivalent to 88 days here. That's just over 2 months here. So this thing is going 29 miles a second. That's insane. Okay, that's why it got its name. When we're looking at radius, the reason I have these out here, so when you go back and look at your notes, you can compare the radii of the different planets. You can kind of get a sense of where they are in the placement of like largest to smallest. Okay. Remember we talked about sunlight for reaching the different planets. Here on Earth, it takes about 8 minutes, give or take, for the sunlight to reach us. And we also talked about distances in the solar system. So remember, an astronomical unit, 1 AU is Earth to the sun. That's our basis of comparison. So obviously Mercury is much closer to the sun, so it is going to be a smaller number than 1. And in this case, it is 0.4. Now, it is also the second most dense planet. So we believe there's a metallic core, could be molten, could be liquid to an extent. We're not 100% sure. We're still learning more about Mercury. Okay, but I just don't think it's the coolest planet out there. So here's some of the exploration we've done for Mercury. I also tried to include that in these slides because it is really cool to think about how we got this information. And, are we going to get any more information in the future? How do we get more information? What kind of information do we need? Things like that. So back in the 70s, we had Mariner 10. This took the first picture back in 74. It was the first spacecraft sent to Mercury. So, woo, go Mariner 10. It did a lot of flybys of Mercury, so that's where it kind of does like loops around it, or like zoom in and kind of go far away, come back, zoom in, basically passes at it so it can get lots of different data. And this was the first time we also used a gravity assist to change a flight path. This is huge, especially when we're talking about the future of space exploration, even going into modern times. because even the upcoming mission Artemis 2 is going to use a type of gravity assist to help with its flight path. Gravity assists are a huge, huge thing when we're talking orbital mechanics and astrodynamics. So the reason we sent Mariner 10 is we had this goal of studying its supposed atmosphere. We wanted to find out more about what was on the surface and what kind of characteristics it had. And of course, we started to catalog these things. Then we had the Messenger program, the full name, full government name, if you will, Mercury Surface Space Environment Geochemistry and Ranging. This is why NASA loves acronyms. All the names are very, very long, but they get the point across of what they do. Okay, so just from the name, you can see it's going to look at something geo, so Earth, chemistry, chemicals, surface composition, things like that. It's going to look at the environment, the surface. It's telling you what it's doing. It's just a very long name. This was active from 2004 to 2015, and so it orbited the planet continuously for 4 years. The longer a spacecraft is in orbit around a planet, especially if it's more of a fixed orbit, we can get more and more data from that, as opposed to flybys, which are usually like quick bursts of data. An orbiter is going to give you a lot more information. So I was able to figure out the surface composition, a little bit of the history of the geo or the surface. It looked at the internal magnetic field, and it did confirm that there is water ice up in the poles. That's pretty cool. And then the most recent is Ms.B Colombo. So this is a flyby and an orbiter, 2 different types of missions. Okay, these are words you're also going to see me use a lot through this slideshows because they are different kinds of missions. So we launched this one in 2018. It did its first flyby in 2021 and started orbiting pretty recently, a couple months ago, December 2025. So this is the first 2 were NASA missions. Okay. This is actually an international mission. It's specifically with the ESA, which is the European Space Agency, and JAXA, the Japanese Space Agency. So they work together. A lot of the other space programs out in the world are smaller than NASA, especially when you're talking about like the Europeans. A lot of those countries are too small to have their own standalone space program, so they came together into the ESA. And a lot of times what happens here is these programs work together to, pool their money, pool their resources, pool their scientists to build these great spacecraft and these different missions. And NASA does this as well. We work with the Canadians, we work with ESA, we work with JAXA, we work with Roscosmos. There's lots of different space agencies out there. And the whole point of space is to be beneficial and open to all. So it is not a, oh, you're from a different country, I can't talk to you game. That's not the point of space. So ESA, they specifically designed the Mercury Planetary Orbiter, or the MPO, to study the planet's surface and its interior, whereas the Japanese designed the Mercury Magnetosphere Orbiter to study the magnetic field. And you're probably going, neither of those things, MPO or MIO, are found in the name Ms.B Colombo. Like Messenger makes sense, right? It's an abbreviation, it's an acronym. You're probably going, what? Well, what happened here is it was named after an Italian mathematician, engineer, and professor whose name was Giuseppe or Beppe Colombo, who was present from 1920 to 1984. So here's some cool images I found. So this is kind of a diagram of the Mariner. You can see it's cool and labeled and all that. You can see some other missions like this. These are artistic interpretations, especially this one here. But you can see it's like on approach to Mercury. It's, that's pretty cool. Okay, second planet from the sun, aka Earth's evil twin, Venus, named for the goddess of love, Aphrodite, or Venus, depending on which version of mythology you like. Again, not a full 1 AU from the sun because it's still closer than us, so it's 0.72. So sunlight gets there a little bit faster. And if you look up in the nighttime sky, if you're looking for Venus when it's out, it is actually quite bright and distinct to see. It is actually the 3rd brightest object in the sky. So keep in mind the first is the sun, the second is the moon, and the 3rd would be Venus. It's kind of crazy. That's how bright this thing is. And guess what? Our ancient ancestors, when they were looking up in the sky, making all these stories with the constellations and everything, they noticed Venus. Venus is very easy to notice. And so that's why they made stories about Venus and following it the path through the sky and things like that. Typically speaking, when they came to the ancients, if it was very, very obvious in the nighttime sky, that meant it was important. Okay, Venus does not have a moon. No moons. Sad for Venus. Also does not have any rings. All right. You can look at the diameter there. I put it in miles as well as kilometers because I realize this is an American public education system and we think in miles, not kilometers, because America, even though I am loath to admit it, because I was anti-metric system most of my schooling as well until I started working in research, and suddenly I was like, the metric system is boss. Love metric system. That's a side note. Anywho, what's interesting is on its axis, it doesn't really tilt, kind of like the Earth. It has a tilt to the axis. That's how we get seasons. Venus does not really have a tilt, so it doesn't have noticeable seasons. Now, remember I said most people would assume Mercury is the hottest planet. It doesn't win that award. Venus does, okay? I'll show you the temperatures in a second. But think about what I said about the atmosphere and what it does. It's like a nice warm blanket. Okay, so this you can see in this visible light image, this is all the clouds you see on Venus, all of that dense atmosphere. This is showing you, like through infrared, I believe is how they take this picture. You can see more of the surface features, okay? So while Venus doesn't really have noticeable seasons, it does go through phases. That's one of the things some of our early astronomer scientist folks looked at, which helped confirm Earth is, going around the sun, not the other way around, okay? So 1 year there is about 225 Earth days. That's one revolution, remember? That's still way smaller than an Earth year. A day, however, is very long. Okay. So one rotation, one going all the way around on its axis like a top, is 243 Earth days. That is so long. We would have to completely invent new clocks and calendars and everything if we lived on Venus. All right. And also interesting, it's kind of backwards. Okay, here on Earth, think about which direction the sun rises in. Rises in the east, sets in the west. On Venus, sun rises in the west, sets in the east. So we call that a backwards rotation. Okay. Again, it has a very thick atmosphere. You can see it in this picture versus if we kind of decide the atmosphere away and then we can see the surface features. That's what you're looking at there. So the reason this atmosphere is so thick and the reason Venus gets the prize for being the hottest planet at 900 degrees Fahrenheit, Mercury was, 800-ish. Okay, so it's not a huge difference, but I mean, when you're at that temperature, ow, ew, gross, no. So the part of the reason it happens here is because of this atmosphere. So the atmosphere is very good. It lets in sunlight just like ours does. And it keeps that heat and that radiation there up close to the surface, which is good, think about here on Earth for us to grow plants and, be human and have animals and all that stuff. But the problem is what happened on Venus is something called a runaway greenhouse effect. So too much carbon dioxide and other greenhouse gases built up in the clouds, the atmosphere of Venus, and now they don't let any of that heat back out. Okay, this is why people have been yelling about greenhouse gases and things like that here on Earth, is because the same thing can happen here. So when the sun goes through the atmosphere, the sunlight, the radiation goes through the atmosphere, it comes into contact with the surface, it can bounce back, right? When you reach a saturation point, essentially. The problem is the clouds on Venus hold that back in. Okay, that heat's not getting out. And also in these clouds, you're going to find a lovely compound called sulfuric acid. This is highly corrosive, meaning it can eat through like metal and tissue and, not things you want to happen. Okay. So going along with this, we've got high temperatures. It's raining acid. That atmosphere is also so thick, it's also kind of pushing down in a sense. So it creates extreme pressure. So think of like Venus as a giant pressure cooker. Yay. Okay, that's basically what it is. This is why it's not a high level of interest in terms of human settlements. It's because, well, we have sent missions to Venus, more on that in a second, and it ate them. It ate the robots. It destroyed them within an hour or less. So that does not bode well for humans. So that's why we're looking toward Mars for future settlements for humans, not Venus, even though Venus would be better in terms of gravitational pull. because our bodies would be basically closer to adapted to it because it's a very subtle difference. But when you think about gravitational pull versus angry clouds that want to smother you, we know the surface has volcanoes. It's got mountains. We know there used to be oceans, as in liquid water, on Venus. And again, the surface features are pretty cool. So these are named, again, keeping in with the theme. So the whole planet is named after the goddess of love. The planets are named after other mythological and real women. So there is a volcanic crater named Sacagawea. There is a canyon called Diana. That, depending on your interpretation of Diana, that could be the goddess of the hunt. That could be Princess Diana. I think it's over the goddess, but Princess Di was wonderful. So we also know it has an iron core, which is surrounded by a hot rock mantle, which also has a thin crust. Sounds kind of familiar if you know your Earth history or your Earth geology. Okay, so we think there might also be plate tectonics like here on Earth. Remember, plate tectonics are how we get different volcanoes and mountain ranges and things like that forming over time. That's how we have earthquakes, all that good stuff. So different missions that we have sent to Venus. Okay, so for the NASA, this time I broke it up by NASA, USSR, aka Roscosmos, and the Europeans. Okay, so in NASA we had Mariner 2, Pioneer Venus 1, not to be confused with Pioneer, which is 10 and 11, which are related to other planets later on. And then we had Magellan. So you can kind of skim these and look at them. All right. So Mariner 2 was our first successful planetary science mission. Woo, go us. It did a flyby in 62 for a whopping 42-minute scan of the planet. Again, these flybys are not a long period of time to get data. So it told us a little bit about the atmosphere and the surface. Awesome. Good for the 60s. That was great. All right, then we had in the 78, we had the Pioneer Venus 1. This is where it started to orbit Venus. And now we're using radar to map the surface, just like we use radar here on Earth to track storms or look at surface features or even find ancient archaeological sites. Okay, I'm sorry if I'm boring you. This is cool. Okay, what's cool about a lot of these NASA missions, not just for this planet in particular, but as we expand into other planets, they are kind of given an estimation on how long that mission should survive, in a sense. Remember, these are robotic missions. There's nobody there taking care of them. So they kind of say, you know, if we did everything right, they said it should last about 8 months. It lasted 14 years. Talk about a return on an investment. Okay. We got a last signal from it in 1992. Then we had Magellan. So this is going into the era of the space shuttle. Okay, so Atlantis is one of these space shuttles that we had for NASA. And what was great about the space shuttle is it had this big old cargo bay, because the space shuttle itself was massive. You could like fit like a school bus in like the cargo bay. So we actually launched this mission from the cargo bay once it was in orbit. It mapped the entire surface of Venus, figured out its gravitational field, and then eventually it was kind of serving its purpose. And this is not the first time NASA has done this in terms of crashing things into planets. They decided, well, we need more atmospheric data, so we're going to run it into the planet. And on its way down, it's going to get a whole bunch of information for us. That's what it did. Okay, then we need to look at the USSR. Nowadays, they're called Roscosmos. So this is back in the Soviet Union era. They're the ones that get the most infamy for studying Venus because they're the ones that sent us back pretty pictures of the surface from a craft that landed on the surface. So, you know, the ones the planet ate. These are called the Venera missions. Numbers 7 through 14 were successful. The others, not so much. This whole program took place between 1970 and 1982. So 7 gets the notoriety for being the first soft landing on another planet, meaning you didn't just purposely go and splat it into a planet. We purposely landed carefully because we wanted it to stay intact. That's a big difference. 9 and 10 started sending back panoramic images of the surface. 12 gets a standout nomination because it lasted a whole 110 minutes. For a record, 2 hours is 120 minutes, so just shy of 2 hours. Okay, and then 13 sent back the first color images of the surface. That's pretty cool. They also sent up the Vega balloons, which were essentially these giant balloons that were in the atmosphere of Venus to kind of give us more atmospheric and cloud information, because again, we're trying to figure out what is going on with those clouds. Why are they so crazy? And then for the European missions, we had the Venus Express. It did its first orbit back in 2006. It's notable because it was the first European spacecraft to orbit Venus, and it was there to study the atmosphere. It showed hard, conclusive evidence of past oceans on the surface. Also, those sulfuric acid clouds, they have lightning in them. So, you know, a giant pressure cooker where it rains acid and there's lightning. Yay. Fun times. Here's some images from some of the missions. So like here is obviously Mariner 2. This would be at NASA. This is some of the data readouts. Look at this long old piece of paper. That's the data readouts that they had to analyze by hand because this was, you know, pre iPhone, MacBook, whatever computer you use. Okay, here's an artistic interpretation. You can see Venus behind it. And then this is the one that was launched from the space craft Atlantis. So this is the payload bay here. This is Earth. And then here is our little spacecraft being launched. All right, and these are the really cool images I want to show you of the actual surface. So if you kind of look at them, you can kind of see the edge of the actual spacecraft itself. So here's an image from Venera 9. This is Venera 10. Remember, these are black and white. Okay, then we started seeing color images come back. If you notice what color it is, that's because of the atmosphere. It's because of the sulfuric acid and the dense and all the carbon dioxide and all that. So that you can see these panoramic images and they are in color, because you can see that's a little bit different color here, right? Like that's clearly a red. But look at that. This is what an actual surface of another planet looks like. It's kind of crazy and humbling to think about. This is from Venera 14. Again, more panoramic images. You can see the surface. All right, let's talk briefly about Earth. So that there are entire classes you could take just about the geology of Earth and the study of life on Earth, aka biology. And that gets broken into so many different subcategories. So I'm not going to spend too much time on Earth because we live here and I want to talk about the other cool planets. But either way, you need to know it's the third planet from the sun if you didn't already know that. I hope you know that. You need to know it's the only planet with liquid water. Notice I use the word liquid. Okay, that's important. It is the largest of the terrestrial planets, and overall it's the 5th largest planet in the entire solar system. So its name comes from Old English and Germanic, which translates roughly to the ground. Okay. Life began here, as far as we know it, about 3.8 billion years ago. That's billion with a B. We'll talk more about that when we get into the astrobiology unit. We know we are 1 AU away from the sun. We know it takes light about 8 minutes to get here. We know how long a year is. We know how long a day is. These are just part of our life. Okay. We do have a tilt to our axis. Okay, so Earth is, you know, it's not just straight up and down on its axis. It's kind of a tilt, and that's why we get seasons. It's very important. And it does not have rings. Sometimes I wish it did, but it doesn't. The brightest object in our nighttime sky is the moon. That's the only moon it has. There is obviously stuff in the news right now about like we have a second moon. Again, we have a gravitational pull. There are things that come in from the far reaches of the solar system, space rock, space junk, what have you. There's a chance they can be captured by us and hang out for a while. That's fine, but they're not official moons necessarily. Okay. The surface, we also call it the lithosphere. This is where all the life is. Okay, litho, life. That word you probably should have learned in biology. If you were in my biology class, you learned it. Go find your notes. The surface has got volcanoes, mountains, valleys, all these things that make up the plate tectonics, which is why our surface is ever changing. If you've ever looked at anything to do with dinosaurs, you know about like Pangea and all those other supercontinents that don't exist anymore because the continents are moving because of plate tectonics. We have a central core. Then we got a molten mantle around it. And then we got a crust. Sounds familiar. Oceans cover most of our planetary surface. However, most of those are saltwater. So just because we see lots of pretty blue water when we look at a picture of Earth doesn't mean all that is drinkable or usable. Be very careful with that. The atmosphere, if you were to ask anybody on the street for like one of those silly TikTok videos where they go and ask people like, oh, what's this fact? Most people are going to tell you that our atmosphere is mostly oxygen. That's not right. Our atmosphere is 78% nitrogen. Nitrogen is an inert gas. That's good. Okay. Remember we talked about like with the Hindenburg and things like that. If it is a non-inert gas like hydrogen, okay, you're gonna have problems. Okay, I think that's supposed to be an H. I think I typed it there. Whoops. Oh, no, it's supposed to be an O. Yeah. I'll fix it later. Okay, so again, we talked about the atmosphere, why it's important. It's where we get our weather and our climate. Those are not the same thing. Okay. Weather is what's happening outside right now. It's windy. It's Oklahoma. Shocking, I know. Climate is the series or pattern of the weather over time and how it changes. Okay, so like the climate of Oklahoma is generally mild. The climate of Florida is generally hot and humid and wet, right? Not the same thing. It also protects us against solar radiation. We do have a magnetosphere present. Again, that also protects us from different types of radiation, space objects, things like that. That's where we get our magnetic field. So if you are any kind of camper, hiker, backpacker, Boy Scout, Girl Scout, what have you, you've probably used some sort of compass. The reason that compass works is because we have a magnetic field. Mars does not have a magnetic field, which means navigating on Mars is going to be a bugger one day. I don't want to think about that right now. Okay, let's get into Mars. So again, Mars is one of my favorite planets. It is the fourth planet from the sun. It also appears pretty distinctly in the nighttime sky, this time as a bright red point of light. There's a reason it got its name. We call it the red planet for obvious reasons. If you look at it, what color do you see? Red. All right. So it is named for the Roman god of war. All right. If you are familiar more with the Greek side of things, he also goes by Ares. Okay. And so what happened here is the ancients obviously very much noticed the bright red thing in the sky. They noticed it was different. They noticed it moved in respect to the stars and how they didn't move, things like that. So what they did is they looked up at the nighttime sky, they saw this bright red dot and said, oh, that must be a great war god up there. He's covered in blood. So we're going to name after our war god. So that's his name. He's named after the war god. Okay. Even the ancient Egyptians called it Herdesher, meaning the red one. And it's in some of their mythologies. Now, if you look at its moons, it's got two small moons. We'll talk more about them in our next slide set about the moons of the solar system. But basically, the moons, admittedly, they're more than likely captured asteroids. They are very much potato-shaped. They're not very fancy in terms of moons, but they are named after either the war dogs or the sons, depending on which version you look at, of the war god Ares. So that's where they get their names, Phobos and Deimos. We'll talk more about that later. This is one of the most researched and explored planets. I like to joke this is a planet that we have littered with robots. There's nothing living on Mars except our robots. Poor guys, they're probably lonely. And the part of this is because we are very much interested in signs of past life on Mars, as well as the possibility of sending humans to Mars for an extended period of time. So that's what, you wouldn't go on a road trip without doing a little bit of research of where you're going first. Same logic here applies. You don't want to just send somebody and go, hope it works, have fun. No, we want to know where we're going, where we're landing, what kind of resources there are, things like that. So it takes sunlight a whole 13 minutes to get out there. So now we're getting further away. So sunlight's going to take longer. All right. One Martian day, we also call that a sol, S-O-L, not capital S-O-L, the name of the sun, but in the same vein. Okay. We call those sols because the hours is a little bit longer than an Earth day. So for scientists working and any of the space agencies working with any of the robots on Mars, when they are actively up sending commands, looking at data, things like that, they actually have to slowly adjust their time schedules of when they go to bed and wake up and go to work and things like that, because they have to adjust to the sol, to the Martian day, because it's not exactly dollar for dollar on Earth. All right, now 1 year, so remember one trip around the sun is 687 Earth days. For comparison, remember, Earth is 365. So it's got a similar tilt to Earth, about the same degrees, about 25. It does have seasons. Those seasons are longer. But that kind of makes sense because of, think about, the revolution is longer, okay? The rotation is slightly longer. That makes a little sense, right? It's about half the size of Earth, give or take. So going to have less gravitational pull. Over here. Look at the cute little robot with his selfie. I love him. Okay, so as you have already gleaned from the images, it is dry, it is dusty. If you've seen any sort of sci-fi movie, you know there are massive dust storms that can block out the sun for weeks, if not months. Okay, there are volcanoes. In fact, Mars is home to the largest volcano in the entire solar system that goes by the name of Olympus Mons. That volcano, just the bottom, the base of that volcano, is about the size of New Mexico. Just let that sink in for a minute. The bottom of one volcano is the size of one of our U.S. states. It's one of the bigger states, too, when you think about it. It's not like, New Hampshire. Anyhow, Mars also has this really cool canyon. We call it Valles Marineris. A lot of people always go, oh, it's a pasta sauce. No, it's not a pasta sauce. Okay, sounds like it. I get it, but it's not. So think of like the Grand Canyon, and then just go even more crazy. Okay, it is 3,000 miles long. That's about the size of the continental United States from edge to edge. It is, at the widest portion, it is 200 miles wide and goes about 4.3 miles down. That's crazy. I don't remember the specs for the Grand Canyon off the top of my head, but I can assure you it's not that. What's really cool, again, is we have started sending rovers and things like that to areas where it's clear there used to be a river, a lake, some form of liquid water right in that area, because those are very appealing to us to land and send a reconnaissance robot, essentially, to go and collect samples for a future scientist to look at, because we want to know, what did life used to look like there? We know there used to be water on the surface. What happened to it? It does have a very thin atmosphere, but again, so it's not holding in a whole lot of heat. It's not holding in a whole lot of anything. That being said, the temperatures can vary. So again, it does have seasons. It does have an equator. All right. If you are close to the equator in like spring, summerish, it's actually like a nice 60, 70 degrees Fahrenheit outside. It's quite nice. Now, don't go out without your spacesuit because you can't breathe. But anyway, now if you're looking at the coldest temperatures, gets down to negative 225, especially as you get closer and closer to the poles, which are made of dry ice. That's that frozen carbon dioxide. It's the stuff you put in like Halloween punch bowls. You buy it from the supermarket. It's like a big block of like white looking ice, and it gives that like kind of fog effect. That's frozen carbon dioxide. Okay. It does not, this planet does not have a magnetosphere anymore. We think that the loss of the magnetosphere, which could be tied to something happening with its core, we think that has to do with the fact that the atmosphere thinned out, and when the atmosphere thinned out, well, guess what? The water evaporated into space. So if there was life and it was water dependent, whoops. Now, as for what actually caused all this possible chain reaction, I haven't seen a conclusive answer. I think they're kind of bouncing some ideas around, but either way. Now, it doesn't have rings at the moment. Now, if you to go forward in time about 50 million years, one of the moons, Phobos, is currently projected to possibly run into Mars. And it's either going to run into Mars in like one fell swoop and make a big old crater, or the Martian gravity could kind of just like shred it as it comes closer and like make a ring of pieces. So it might have a ring in the future. We'll see. Oh, another word I want to point out to you, we call the surface regolith. Okay. When I talk about the surface, dirt, composition, things like that, I'm talking about the regolith. We also use that term when we're talking about the moon as well. And obviously it gets its red color from the oxidized iron, just like we do here in Oklahoma. The reason we have red dirt is because of rust in our dirt, basically. Same thing on Mars. That's another big glaring error, or proof, I should say, that there was liquid water, because you don't get rust without water. Some cool images. So here's Olympus Mons. So again, here's the base of that gigantic volcano. All right. Here is a rough outline of the U.S. states, continental United States. This giant slash across it, that's Valles Marineris, to kind of put it into perspective of how absurd this canyon is. Here's like a zoom in on it. I found this online. I want to order one of these. This is a zoomed in kind of view of both sides, so to speak, of Mars. It's got all the surface features marked. It's got pretty cool details. I can also bring in my Mars globe and show you it's got some of the details marked as well. Why are we not clicking? There it goes. All right, exploration. Again, this is by no means an extensive list. You'll notice I don't have a ton of facts about each one of these because I could and frankly have taken an entire class over just Martian exploration. So I won't belittle you or relay you with all that. So we've got flybys, we've got orbiters, and we have landers and rovers. So landers, generally speaking, don't move once they get on the surface. They do their little thing in their little area, and then they don't move. Okay. Rovers, they can move around on the surface. Orbiters, we know they're orbiting the planet. Flybys, just kind of quick data get grabs as we zoom by. Okay. So you can look at the flybys in the 60s. We had another one in 2018 to 22. Leave your sister alone. The orbiters, lots of orbiters. It's how we've gotten lots of good data from the surface. We've got lots of good images of the surface. Okay, so there's several that are still active. Look toward the bottom there. And then if you look at landers and rovers, going back to the 70s, we had some really cool ones like Pathfinder, Spirit, and Opportunity. I remember when Opportunity went offline in 2019. I was so sad. See, Curiosity is currently active. It's one of the major ones out there. And also Perseverance is the most recent one we sent there. It's part of the Mars 2020 project. And it came with a little buddy. It came with his little buddy by the name of Ingenuity, which is this little guy over here. That was the first helicopter to fly on Mars. Because they're very curious, can we actually support flight of any kind in such a thin atmosphere? And it turns out you can. It's pretty crazy. So like Perseverance is the one that's been collecting little samples, like little test tubes of samples it drills in where it's told to and gets a little sample and then it leaves it there. So future scientists can go and collect those and study those. Also a cool picture I found online of all the different missions, or most of the different missions. You can see different countries associated with each one. All right, and then in part 2, we will talk about the Jovian planets, or whatever. You know what words I mean. I'll see you in part 2.